Alright, now we're going to go ahead and actually get into our lesson for today. Today we are going to be talking about what are called multiple and half angle equations. We can tell that these equations are different for a couple of reasons. The most obvious is that all of these equations involve functions of half angles or multiple angles, and they often require adjusting the solution interval to fit the given domain. For example, let's say I gave you the problem cosine of x divided by 2 is equal to 0. And I told you that I wanted all solutions to be in the interval from 0 to 360. Alright, so a couple of things to recognize is that first of all, whatever I see done here to my angle is what I want to do here to my interval. So my angle is being divided by 2. Since this right here is being divided by 2, then that's what I want to do in my interval. So I'm going to say divide by 2, divide by 2. And my new domain for my angle has now become 0 to 180. So now when I do this problem and I say, alright, I'm trying to solve for all angles such that the cosine equals 0, I'm only allowed to look in the interval of 0 to 180. So I'm going to do cosine inverse of 0. And normally, cosine inverse of 0 would have two answers. We would have 90 degrees and 270. However, 270 is no longer in this new restricted domain. Therefore, the only answer I get is 90 degrees. And we're almost done. At this point, we get our answer for x halves. Because remember, my problem says cosine of x halves equals 0. So right now, this solution that I got is the answer for x halves. But I want to solve for x. So what I need to do is multiply both sides by 2. And I get that my solution is 180 degrees. Now if we were to plug this into the original problem to check our answer, when we get here we would say cosine of 180 divided by 2 equals cosine of 90 equals 0. And we've done the problem correctly. So basically what we want to remember is that we have to do two things to solve the problem. First, we must adjust our interval. Then we need to solve. And then after we've done that, we need to adjust our solution. So essentially we're adding on an extra step at the beginning and at the end compared to what we did earlier in the week. Alright, so if we take a look at these next few problems, now I have my interval in 0 to 2 pi. Basically the only difference between 0 to 360 and 0 to 2 pi is so that we know which unit our answer should be in. In both of these cases I'm using an x halves is the type of angle I'm dealing with. Therefore my interval needs to be cut in half to match an x halves. So since I divided by 2 on my variable, I divide by 2 on my interval, and I'm going to be in the region of 0 to pi. Alright, so when we go ahead and solve these, we would first isolate the function. So x, or cosine of x halves equals 1/2, and for part B I would have sine of x halves equals 1/2. And then now I go to solve. So when I go to solve, I'm looking only in the interval of 0 to pi. And in the interval of 0 to 2 pi, there is only one angle that has a cosine ratio of 1/2. And that one angle is pi thirds. Now when I compare this to part B, sine has two answers in the interval of 0 to pi that have a sine ratio of 1/2. So for part B, my x halves has two solutions. It has pi 6 or 5 pi 6. And now I can finish the problem by actually solving for x, and the way that I solve for x is by multiplying by 2 on both sides. So for part A, there's only one solution. For part B, when I times both of those by 2, there are actually two solutions. So it depends upon the function whether you're going to have one answer or two in the new restricted domain. Again, let's refresh. We have to first adjust our interval. So we divided our interval of 0 to 2 pi by 2. we solved. We figured out what angles give us that desired ratio, and then we took those answers and we adjusted them so that we were actually solving for x and not just for x halves. Notice in this problem here, I now have a double angle problem. Since my x has been multiplied by 2, my interval needs to be multiplied by 2. So now 2x is in the interval of 0 to 720 degrees. Alright, so now that I've identified my interval, I'm going to go ahead and I'm going to ask myself, when does sine have a ratio of root 3 over 2? And that occurs here and here. And in degrees, that's going to be at my 60 and my 120. Now notice that my interval was all the way to 720. So when I see this 2x, that basically means I'm going to go around the circle twice. So if I add 360 to those answers, I will get my other set of solutions. So right now I have that 2x equals 60 degrees and 120 degrees. And then if I go around the circle again and add 360, I will get the answers of 420 and 480. So I first adjusted my interval, then I solved my problem. Last, I have to finish it off and divide all of these by 2 so that I can actually solve for x. So my solutions are 30 degrees, 60 degrees, 210, and 240. And I want to point out that after we have solved for x, these solutions are all now in the original domain for x. Okay, so we adjust the domain, we solve the problem, and then we readjust the solution so that it matches the restrictions of the given problem. Alright, pause the video and go ahead and try number 3 on your own. Okay, in this problem we have a 3x, which means that we need to triple our interval and go around the circle 3 times. So my original starting solutions are going to be from 0 to 6 pi. So I start by saying, okay, I know that cotangent has a ratio of root 3 at pi 6 and 7 pi 6. Now that's one time around the circle. To go around the circle again, I add 2 pi to each of those answers, or add 12 sixths, which gives me 13 sixths and 19 pi 6. And then I do that one more time, adding 12 sixths to those second set of answers, give me 25 pi 6, and lastly 31 pi 6. Now these are all my solutions for 3x. To solve for only x, I need to divide all of them by 3, giving me solutions of pi 18ths, 7 pi 18ths, 13 pi 18ths, 19 pi 18ths, and so on. At first glance, you probably want to take your interval of 0 to 360 and double it to get 0 to 720. However, that is not what you want to do. And the reason why is because this problem not only has a cosine 2x, but it also has a cosine x. And we cannot solve our problem if we don't have the same variable in all of those trig functions. We just don't know how to handle that. So instead what we can do is we can go ahead and we can expand the cosine 2x using those identities that we learned last chapter. And when you're trying to figure out which identity to use, I would recommend using the identity that only had cosine in it, so that way we now have a quadratic equation that only is in terms of cosines. So now we can go ahead and we can set it equal to 0. And then we can factor this. Alright, pause the video and complete this on your own. As you can see, this factors nicely, and we now have 2 factors that we have to solve for. We set each of these equal to 0, and we can go ahead and solve just like we were doing in section 6.2. We have a total of 3 answers here. Now one of the things that you have to be careful of is, just like before, if we end up getting solutions to one function that don't work in another function, we need to check that. However, cosine is never undefined, so we don't really run into that here. Also pay attention that my solutions are still in the interval of 0 to 360. At this point up here, when we expanded at cosine of 2x, we no longer have a double angle identity, so we no longer have to double the interval. Pause the video and try example 5 on your own. You should get a total of 2 solutions. Alright, so in this problem we need to remember to reduce our interval to be from 0 to 180. We have to divide by 2. After that, we isolate our trig function, and after rationalizing and simplifying, we see that this is equal to root 3 over 2. And our sine function is equal to the ratio root 3 over 2 at our 60 and 120 degree angle. And then from here, we simply multiply those angles by 2 to get back to the solutions for the original theta that we were working with. This problem here is pretty challenging, mainly because we have 2 different functions, and in addition to that, we also have a double angle function. Now I'm going to show you kind of a neat way that we can solve this, just to give you an idea of some alternative strategies we can use. So instead of trying to expand out this cosine of 2 theta, what I want you to recognize is that over here on the right, this is equal to 4 times 2 sine theta cosine theta, and 2 sine theta cosine theta is the same thing as sine of 2 theta. So right now we have cosine of 2 theta and sine of 2 theta in the same problem. And the 4's can cancel off, so we divide by 4, those go away. And then if we go ahead and divide the cosine 2 theta to the other side, we can have 1 equals sine of 2 theta over cosine of 2 theta. And another way of thinking about sine over cosine is to say that 1 is equal to tangent of 2 theta. Now this equation right here is a heck of a lot easier to solve than what we started with. So at this point we say, okay, it's a 2 theta, therefore I need to double my interval of 0 to 720, and I'm looking for where my tangent ratio is equal to 1. Now we know that that occurs at the 45 and the 225, so we can start by saying that 2 theta equals 45 and 225, and then again, because it is 2 theta, that means we go around the circle another time, so we have to add 360 to those solutions to get 405 and 585, and then from there we have to get them in terms of theta by dividing by 2, and that's going to give us 22.5, 112.5, 202.5, and 292.5 degrees. And you could also leave those in fractions, 45 halves, 225 halves, and so on. Alright, there's Math Excel homework for tonight. Go ahead and give that a try.